Back in 2017, a small group of researchers published a paper with a title that was, deceptively simple. I don't think they had any idea it would basically become the Big Bang for the entire generative AI revolution that we're all living through today. So let's dive into the paper that really did change everything. Attention is all you need. See, this wasn't just some catchy title. It was the paper's entire radical argument, all packed into 5 words. The authors were making this incredibly bold claim that one single mechanism, attention, was pretty much all you needed to build the most powerful language models the world had ever seen. And, well, they were right. Now, to really get why this paper was so revolutionary, we have to kind of rewind the clock to the world of AI back in the mid-2010s. Language models were already pretty powerful, but they were hitting a wall, and hitting it hard. There was this fundamental bottleneck that was seriously holding back progress. So before this paper came along, the best models processed language sequentially. I mean, just like you'd read a sentence from left to right, they would process the first word, then the second, then the third, and they'd try to carry a little bit of memory along the way. You had these models, recurrent neural networks, or RNNs, and their more advanced cousins, LSTMs and GRUs, and they were the undisputed kings of things like machine translation. They were absolutely state-of-the-art. But this whole one word at a time thing, it came with a critical built-in flaw. Now, this table looks a little technical, but stick with me, because the really important bit is that sequential operations column. For a recurrent model, the number of steps it takes is directly tied to the length of the sentence, what they call N, and that meant 2 huge problems. First, they were slow. And second, by the time they got to the end of a really long sentence, they'd often forgotten what happened at the beginning. This was the bottleneck. So the authors of Attention is All You Need looked at this whole sequential problem, and they proposed something that, at the time, seemed just completely out there. They decided not to just fix the bottleneck, but to basically blow it up entirely. This one sentence from the paper's abstract is pretty much a declaration of war on the old way of doing things, based solely on attention mechanisms, dispensing with recurrence entirely. I mean, they were just throwing out the core established building blocks of language AI and starting completely from scratch with this one single idea. The idea was to just abandon that linear word-by-word chain. Instead, they would feed the model the entire sentence all at once and just let every single word make a direct connection with every other word. It wasn't a chain anymore, it was more like a fully connected web. And the architecture they designed to actually do this is the hero of our story, the transformer. This is the engine that powers pretty much all of modern AI. Now, on the surface, the transformer uses a classic encoder-decoder structure. That part wasn't new, it was pretty common at the time, but the real revolution, the magic, was what the authors put inside of it. So the encoder's job is basically to read the input sentence, let's say in English, and build this really rich numerical understanding of what it means. Then, the decoder's job is to take that understanding and start generating the output sentence, say in German, one word at a time. Okay, so let's peek under the hood. The transformer is built from a stack of layers, and inside each one is that key mechanism, multi-head attention. But wait a minute, look at that last point. If they threw out sequential processing, how does the model know that the dog bit the man is different from the man bit the dog? That's where positional encodings come in. They're basically little signals, like a zip code, added to each word that gives it a unique address, preserving the original order of the sentence. All right, so let's talk about that secret sauce, self-attention. How does it actually let a word figure out its own context inside a sentence? So the paper defines it as a mechanism for relating different positions of a single sequence. In plain English, that just means for every word it's processing, the model gets to look at all the other words in the sentence and decide which ones are most important for understanding that one specific word. The way the paper explains this is just brilliant, using this analogy of queries, keys, and values. It's like this incredible dance that happens all at once. For every single word, it sends out a query, kind of like asking, hey, what's my context here? At the exact same time, all the other words offer up a key that describes their role. The model instantly calculates a score based on how relevant they are, and then it pulls in the values, the actual meaning, from the words that matter most. The result is a brand new understanding of the original word, but now it's totally rich with context. And here's the kicker. Because every single word is doing this query key value dance at the exact same time, the entire process is massively parallel. There's no more waiting in line, one word at a time. The sequential bottleneck was just gone. So the theory was beautiful, right? But did it actually work? Well, the results section of this paper delivered an absolute knockout punch to the old way of doing things. 28.4. This was the Transformers' new state-of-the-art score for English to German translation. Now, to put that in perspective, it was over 2 full points higher than the best models that came before it. In the world of machine translation, getting an improvement that big from a single new model it was unheard of. And not only was it better, it was just unbelievably more efficient. I mean, look at this chart. It shows how much computer power it took to train these models. Look at that tiny little bar for the transformer. It's at a new record while using a tiny fraction, in some cases less than a tenth, of the computational power. It wasn't just better, it was better and way faster. And the hits just kept on coming. It set a new record for English to French translation, too. They could train the big version of the model in just 3.5 days on only 8 GPUs, which was pretty accessible even back then. And just to prove it wasn't a one-trick pony, they threw at a totally different grammar task, and it did surprisingly well, which just showed how powerful and versatile this new architecture really was. You can imagine the impact of these results was immediate and, well, profound. This paper didn't just nudge the field forward, it gave it a completely new foundation to build on. I mean, look at how fast everything happened after this. Within a year, the Transformer was the go-to architecture for pretty much all major AI language research. By 2020, it was the undisputed foundation for this new thing called large language models. And from 2021 on, that foundation has supported the absolute explosion in generative AI that we're all using today. And this is really the key takeaway here. Every single time you use ChatGPT or Gemini or Claude or any of these other incredible AI tools, you are using a direct descendant of the architecture that was laid out in this one paper from 2017. It's literally the DNA of modern AI. This single paper completely redefined what was possible in artificial intelligence. It solved a fundamental problem and just unleashed this wave of innovation that is still picking up speed today. And it leaves all of us with a really fascinating question. What's the next bottleneck? And are we maybe just one brilliant paper away from solving it?